Alright, so let's pick up with program transformations. So if you like, this is sort of an application area of the equivalence ideas that we've been talking about. And the idea is that if you have a transformation that turns a program fragment into another program fragment of the same kind, you want to be able to make some assertions about the behavior of the original program with respect to the transformed program. And in particular, in this version here, we're going to talk about soundness. So the idea of soundness is that if you do a transformation, then the transformed program respects the behavior of or preserves the behavior of the original program. It's not necessarily all you would want, but this is one requirement that you typically would want of one of these transformations. So for the imp language, we can define these properties here, and if you look at the argument here, each one of these arguments is a transformation function. So a program transformation in this setting is just a function from, in this case, arithmetic expressions to arithmetic expressions. Doesn't matter what that function does, as long as it takes in expressions and produces expressions. We can talk about it as a transformation. And we have a Boolean expression version and a command version of that idea. And then the soundness is just saying that it doesn't matter what expression you give to the transformation, the input, the original expression, is equivalent to the output of this transformation function. Right? And the important part here is that this is quantified over every possible arithmetic expression. So again, this is a much stronger result than testing can give you. So we can test transformations to see that they produce equivalent things, but this is saying it doesn't matter what crazy expression we come up with, nothing can go wrong with the transformation. Okay, so this is just a property, so this is really saying what it means for a transformation to be sound in each of the three different kinds of program construct that we have. But it doesn't say anything about any particular transformation. It doesn't prove anything. It's just a statement of the property. So the next part here is we're going to look at a particular transformation and prove that it's sound. So constant folding is a typical compiler optimization that happens quite a lot in commercial compilers and so on. Basically, it says if you can look at an expression and sort of work out that some part of it is constant, it means that in theory you can calculate the value of that expression at compile time rather than generating code that would calculate it at runtime. So constant folding is basically looking for constant expressions, and if it can find some, it's folding the expressions. In other words, it's applying the operations of the expressions to actually calculate the answers of various expressions and replacing the expressions with their results. Now, obviously, in an expression, so this particular version here is for arithmetic expressions. There's a limit that it's not going to be able to fold things, for example, that have variables in them, right, in general. So there are other optimizations that might apply for things with variables in them, but variables are not constant by definition. So if you've got x plus 1, you can't simplify the x plus 1 into something else. You've got to leave it there. Whereas if you've got 2 plus 1, you can turn that into 3 without any trouble. Okay, so first step is to define the transformation function itself. So that's this fold constants ax here. And it's a recursive function, which probably shouldn't surprise you, with one case for each of the constructors in the ax type. And we basically have to just recursively fold things as we find them. So in this case, the numeric expression doesn't change because the value is already as simple as it can be. Similarly, an identifier variable reference doesn't change either because it's not able to be changed either. But for pluses, minuses, and multiplications, we can potentially fold things. And the way this works for each of them is we take the two sub-expressions and fold them to make them as simple as possible. So we're matching on the output of the recursive calls here. And then we look at the output, and if the output of a recursive call is a number for both of the expressions, then we can fold. So we can return a number which is the sum of the two individual numbers. And so in this way, the a plus that was there before is replaced by an a num of the sum. But this is only valid if the sub-expressions fold to numbers. If they don't, then the second case applies. So the folding might fold one of them to a number, but the other one not, or so on and so forth. Then we just leave the plus in place, and we use the values that the children folded to as the pieces. And that's important because it might be that somewhere deeper inside A1 and A2 something has been folded, but the top level of A1 hasn't been folded away. So we need to use the recursive values here. The same thing in work goes for minus and plus as well. The only difference is that in operator position you're using the relevant operator. There is one side question that compiler writers have to care about here, which we're not going to worry about, which is that there may be a difference between the notion of plus for the language that you're compiling and the notion of plus for the implementation language of the compiler. And if you do this sort of folding operation, you're really saying that they need to be the same thing, because it wouldn't do to have a notion of plus that does some particular form of addition and another notion of plus that is used by the compiler, because then this number in here might be the wrong number for the particular program, and you might get a different result from an optimized version of the program versus an unoptimized version. Typical case where that might apply is things like overflow. So if this computation here overflows in the compiler code but doesn't overflow in the implementation code, then you get a different outcome for the computation. For this compiler, we're assuming that they're the same semantics, and the normal Coq definition of plus, minus, and mult is the right one to use for the imp plus, minus, and mult. So that's a simplifying assumption. Okay, so if we have that function, then we can just apply it to arithmetic expressions. So in this case here we have an expression that is 1 plus 2 on the inside here multiplied by x. So we can see that the 1 plus 2 is a constant sub-expression, so it can be replaced by 3, but the a mult and the x can't change, so they're left in place. And this is just a matter of cranking the handle on that function, and you get the right answer out. So this is just a basic test that the function is actually working. So this example is just showing that if you have things like so multiplication, so this multiply here will get folded, right? 0 times 6 is 0, but then you've got a plus 0 and y, right? But that won't get folded because the y is not a constant. And that's where some other optimization would want to come in and say, well, I know that 0 plus anything is anything, so this could be further optimized. But in this constant folding operation is not going to do that kind of folding. It's only going to fold if you've got two nums, so that this one doesn't get folded here. Now we can take that same idea and apply it to folding Boolean expressions. So this function is a bit longer because there are more constructors around, but basically you can apply the same approach and say if there's a way of folding a sub-expression, then maybe you can do one of the operations straight away. So for example, in equality, we can fold the arithmetic expressions, which is these two, and then see if we already know what those numbers are. And then we can replace the BQ with either a true or a false, depending on if those N1 and N2 are the same, using BQ nap. Okay. Otherwise, we replace it with the sub things, but we leave the EQ in place. Same for less than or equal to. Not. We're folding recursively a Boolean expression, so if we get true, we turn it into false. If we get false, we turn it into true. Otherwise, we'll leave the not. Similarly for AND, if we know what the Boolean result of both operands is, we can replace it by the result of the AND. And just like the arithmetic expression one, this is essentially a bottom-up process, since we're calling the recursive cases before we do the assembly. Okay, so in this case, folding a Boolean expression here, we've got AND true, not and false true, so this is going to be false, not false is true, and true is true, so this folds away to just be true. Okay. And similarly, this one's a bit harder to see, but if you've got here, say, this bit can't be folded because it's using some variables. This bit here is basically subtracting 1 plus 1 from 2, so that's going to be 0, so that we'll get the two zeros are equal, so we'll get and true here, which is the result we get. And again, we could, if we're doing a different other optimizations, we would probably remove the true, because and true is just, or x and true is just x. So this is only a partial optimization, but it's enough for our purposes. So you get the idea. The same applies for commands. So we've got fold constants com, which says the same sort of thing. We're inside assignment statements, we can fold the right-hand sides. Inside an if, we can fold the Boolean. If it turns into true or false, we can then just throw away the if and then fold the appropriate branch. And similarly for whiles, if we get true, we just replace it with a trivial infinite loop. If we get false, we just replace it with skip. Otherwise, we leave the while in place and fold the body. So the details there, you can have a look at it. So this is the biggest example of a folding case. So we've got this long program here, and we're just going throughout the whole program folding as much as we possibly can. So what happens? So the a plus 4, 5 here turns into 9. The y becomes x minus 3 is unchanged. The condition here gets simplified a little bit because there's an a plus 2, 4 there, which turns into a 6. I think the body of this is the same. There's a little bit of extra funny formatting going on, but it's the same construct. Yeah, so where does this come from? Well, it comes from this if here. Basically, the if condition is a constant, so we can work out whether it's true or false. It turns out to be true, so we replace the whole if with the true branch, like so. We don't need to test the condition at all. And the while loop, I think, stays unchanged. Okay, so if you take those three functions sort of working cooperatively, you can just feed any program, any command do them, and you'll get an optimized version. So in this case, it's done some simple expression optimization, but it's removed a whole if statement, for example, which is a good thing. Okay, so we've written the soundness, we've written the transformation, but how do we know it's any good? And by good in this context, we need to know that it's not going to make some mistakes somewhere. So we don't want it to replace a plus with a multiplication, or swap the arguments of a subtraction around the wrong way or something like that. So that's where these sorts of soundness proofs come in. So remember, soundness for A-transes was basically saying for a function, for every expression I feed at this, the expression is equivalent to the output of this function. Okay, so that's what this proof is doing. Now it's a little bit hard to visualize what's going on because they use a bit of optimization of everything here, but I'll just change this as we go just to show you what it looks like. So notice how we've got 5 sub-goals now, because we've got one for each of the kinds of arithmetic expression, because we're doing induction on A, which is the expression that we're talking about. The first 2 are easy because they're just already equal. So that's why the first step in this proof is try reflexivity. So that dispatches the numeric case and the identifier case. So now we've only got 3 goals, 1 for plus, 1 for minus, and 1 for multiply. And you sort of see the pattern of what's going on here. So they've got a match on the first folding with a nested match on the second folding, and then eventually it's going to give us back the result. But we've also got this information about what happens to that this soundness result holds for A1 and for A2. So this is saying that if you fold A1, you get something that's equivalent to A1, and if you fold A2, you get something equivalent to A2. So we're going to need to use all of those. This whole thing is quite messy written the way it is. So let's just do one of these directly. So if we say that, so I'm just doing the plus case. So now we've got 7 sub-goals. Why is that? Well, that's because the result of the folding of the excuse me, the result of folding the A1 has now given us cases for all the possible outcomes of that. And if we do the structure of the other one, now we've got 27 sub-goals, so we've sort of spread out all the different combinations of things, right? This is where the proofs get more complicated, and that's why you really want a proof tool like this to help you keep track of everything. But if you see, say, this first one, we now have to show that the sum of the evaluations of the 2 sub-expressions is equal to the thing that the constant folding thing came up with, right? And we can just use these inductive hypotheses to do that. So if we do a rewrite using both of those, we now get something that looks like this, right? And if we think about what A-eval does to nums, right? The evaluation of a number thing is just the number. So this is just going to be n plus n0, and this is just going to be n plus n0. So that's going to be enough to solve that. So we can just simplify essentially. But well, let's do the simple first. Okay, so you can see we've got a lot of things that look the same. So reflexivity will okay. Now it's only done one of those, so now we've got the minus case. So if I turn the dot up here into a semicolon, it will apply that for that. I don't know why there's a try here, to be honest. It's protecting against something, but I don't think there's anything to protect against. So the proof works without the try. Okay, so there's a lot going on here, I understand, and this is where you really need to be clear on what all these different things are doing. But we're really just manipulating the structure of programs and having the bookkeeping take care of lots of different cases for us, which is quite useful. In this case, we've got up to 27 cases in there, so it's we're not going to keep track of that by hand very easily. So this shows us that this fold constants AX has the desirable property that it doesn't change the meaning, the behavioral properties of the expression when it does the transformation. So I'm not going to go through the rest of these things. So they go on and they do the same process essentially for the Boolean expression one, which is this proof. Okay, and this one is the command one with a few holes to fill in because it's an exercise. So, please have a look at those proofs and sort of probably the Boolean one is the best one to look at since it's similar to the other one, just to make sure you understand what's happening here. Okay, so I'll stop on this part and come back with the last part.